Hello, today I would like to share with you the story of Spin by Sin-itiro Tomonaga. Um, Tomonaga was one of the three people, there's a picture of him right there, one of the three people who shared the Nobel Prize in 1965 for quantum electrodynamics. The other two are Julian Schwinger and, of course, um, Richard Feynman. So this is basically a story of the sort of things that he did, and it's a story of spin. Now, this is a particular quantum property of elementary particles. You might remember that from a quantum mechanics class or a modern physics class or even chemistry class. That, something like the electron has a mass, right? It has a charge and it has a spin. You have those things, you basically have everything you need to know about your electron as an elementary particle, or as something that you're going to actually worry about in determining its dynamics and things like that. So if you want to put together your Hamiltonian, you need to know spin, which is basically the magnetic moment of your little electron. So your electron is going to interact with its mass, so it's going to interact with, I guess now, your Higgs field and your gravitational field. The electron has a charge, so it's going to interact with the electric field and magnetic moment, so the magnetic field. Obviously, the electromagnetic field is just one thing, but it's got the two different things going on in there. That spin is why you have permanent magnets. And we'll talk about that in a little while. So you'll notice if you have only taken like a physics 2 class or something like that, they start off talking about, we're going to explain why your refrigerator, why your magnets stick to your refrigerator and things like that. And they never really do. And people come out of that with some really weird ideas like all metals are ferromagnetic and stuff like that. I don't know why people get that idea, but I've heard that a lot from people who've taken, freshman physics. They still sort of only get the idea that metals are magnetic. Well, it's not metals, right? It's not conductors that are magnetic. It's basically things with iron, cobalt, and nickel in them. There are some other elements, but that's a little more rare. And usually when you have those are those other elements that are highly magnetic or almost magnetic. These are generally additives to iron, right, or cobalt or nickel, but usually iron is the big one. Nickel has a lot of really good properties, but iron is a stronger one in general. So this is that story of spin. It is not really your normal textbook, but it is not a, I want to get a good page here. It is not a popular book on physics. So you just look at this page here, you got nice diagrams. These are the kind of diagrams that physicists love to look at. Actually, this particular diagram you've probably seen in chemistry. But, you have your energy level diagrams, you have differences between symmetric and anti-symmetric wave functions and things like that. This book requires a little bit of background knowledge, so it's probably not something you want to go out and get if you've only had that one freshman level year-long survey, right? It's something that maybe after you've taken your junior level quantum mechanics class, you can take to try to figure out what that spin was, right? So, I mean, if you had Securi or what was it? There's another one that does the same thing. But some of these quantum mechanics texts, Townsend's the other one. Some of these quantum mechanics texts really look at spin early on because you can explain some of the probabilistic nature and you can explain the measurement problem in physics fairly easy with the spin if you don't get into too much detail, right? It's very strange. I mean, some people think spin is really hard, and that's because usually if you introduce spin later, you start introducing spherical harmonics and other really nasty stuff with it. But if you are just looking at the interaction of an electron with a magnetic field, then the spin's actually fairly simple. You can construct a pretty simple Hamiltonian and explain a lot of things in quantum mechanics with it, right? Without having to talk about the Schrodinger equation and very difficult topics like that. So this is a really nice book if you're at that level, if you want to look at things at that level. If you can, even if you can, just read equations like prose. If you can write a poem in mathematics, this is a book for you. All right. It's a history book, really. It's a history of spin, the story of spin. You should be able to figure that out. And it's very nice. I really love this book. It's from like a 1974 set of lectures that was published in English in 1997. And I really enjoyed reading it. I'm not exactly sure when I got it. I think I read it first when I was in graduate school, and I may have read it a second time a little bit later. I'm not completely sure. I think I did read it a second time, but you can see this is in this strange time when I couldn't get the kind of contact paper I like on these books. Maybe you can't see it. I'm looking up at the screen. You can't see that, the contact paper on this book's a little bit different from the other kind of contact paper, and it has some errors that I dislike. The other contact paper is a little bit better. Probably I shouldn't talk to you about that, but there's a tip. Paperback books are much better than false hardcover books. Real hardcover, sewn bindings, those are good, but if you don't have those, paperback books are better, except, the cover is paper, but you put a little bit of contact paper on top. Cut it around like this. They last forever, or they last at least as long as the hardcover, false hardcovers that have the glued is it glued or glued? Glued bindings. Okay, so let's take a peek at the contents here. Let's see what was going on here. So, like I said, this is a story, right? The story of spin. This is a history book, so it's going to go basically in order with different problems and try to explain what's going on. So start with lecture 1. People have discovered the Zeeman effect, right? So we've discovered that in your spectroscopy of atoms, if you put a magnetic field on the atom, then you get some splitting, right? You get splitting of those energy levels for some reason. Nobody knows why. Nobody knows why at this time. Nobody knows that electrons have a magnetic moment. This is basically what's going to cause the splitting of the energy levels. And that magnetic moment comes from this thing called spin. We don't know what that is, right? It's just quantum property, but it's not spin yet. Nobody's decided that yet. We have to wait till lecture 2. I think it's Pauli decides that you have a self-rotating electron. Right, so the electron has a rotation just like the Earth has a rotation, right? So not only does it, if you're looking at the Bohr picture, not only does it rotate around like a planet, it also has rotate around the nucleus like a planet. It also rotates around its center of mass. This is a bit of a problem, right? Because as far as we know, the electron has no size, right? It only has a mass. Has a charge and a spin, so it has no size. I think the current limit is 10 to the minus 22 meters. Okay, so much smaller than the nucleus, right? Much smaller than the size of a proton, but still many times larger than the Planck length, right? So it's somewhere between the Planck length probably and 10 to the minus 22 meters, which is a pretty big, 13 orders of magnitude. There's plenty of room in there for, the electron to have a size and so forth. But right now, as far as we know, the electron is a point particle, whatever that would mean when you get smaller and smaller and smaller. But, we have this self-rotating electron idea, and it didn't quite work, but Thomas, I forgot Thomas's name, Llewellyn H. Thomas, same guy with Thomas precession. Actually, I think this is Thomas precession. Applied relativity to that rotating electron, and then you get something a little better. You get a factor of 1/2, I think, or maybe a factor of 2. I think it's a factor of 1/2 that makes Pauli's model work, right? In lecture 3, it says Pauli spin theory and the Dirac theory. Basically, what this is going to do is it's going to push us into the Dirac equation. The Dirac equation is, of course, the basic equation for the electron and the positron. That's how the positron was developed. But that equation includes the spin. The spin is important in that equation. Then we go into the proton spin. And we figure that out. It says here it's determined from a very unexpected problem. That problem is the problem of orthohydrogen and perihydrogen. I hope I get these two right. Orthohydrogen, I believe, has aligned spins, and perihydrogen has anti-aligned spins. But if you don't know the proton has a spin, how can you explain the two different species, right? So we're using that spin now to determine something. You'll determine something about the proton that we didn't know before, right? First we said the electron has a spin. Now we're saying the proton has a spin. That's going to mean a lot of things for statistics and stuff like that. Lecture 5 is interactions between spins. This is basically ferromagnetism, the Heisenberg Hamiltonian. This is the whole reason why we have ferromagnetism and more exotic kinds of magnetism like antiferromagnetism. And not so much paramagnetism. Paramagnetism and diamagnetism, you don't have to use that idea with, but for anything that has some order in it, for any magnet that has order, you need that Heisenberg Hamiltonian, and the amount of coupling determines if you get aligned spins or anti-aligned spins. Ferromagnetism, all the spins end up being aligned. That's the lowest energy state, and that's the reason why they hold a magnetic moment, because they need to have that, because the lowest energy state for a ferromagnet, because of the exchange integral, because of the Heisenberg Hamiltonian, is to have aligned states. What do I mean by an exchange integral? What I'm saying is that there's a chance, if you have these two iron atoms, let's say, each iron atom has, an unpaired electron. That's why it has that extra spin. And those unpaired electrons have an overlap, right? So that overlap has some overlap of the wave functions, and basically the strength of your ferromagnetism is proportional to the overlap between those, because there's a chance that even though electrons aren't doing spinning around things, there's a chance that the electrons will switch. They'll flip from the left-hand atom to the right-hand atom and vice versa. And when they flip like that, because there's an exchange or there's a overlap in their wave functions, that basically gives you that chance to flip like that gives you your ferromagnetism. And this is where the electron is a fermion with a spin. This is where we get the idea that that electron really does have that spin, and it's a quantum mechanical property. That's its magnetic moment. It is not just the electron spinning. Then we go off, and here we have a rejection of the Klein-Gordon equation, which is also a relativistic quantum mechanical equation. I don't want to go into too much detail because I think I know something, but I'm not sure if I'm correct. Uh, this Yukawa particle, basically, this is a boson. This is basically, um, you know, the fact that forces are transmitted by exchanges of particles. Okay, this is this idea that Yukawa had, and this is what lecture 6 is about, is how that works. This is building up towards quantum electrodynamics. The quantity that is neither a vector nor a tensor. This is about a mathematical thing called a spinor. And if you've seen the spin matrices and stuff like that, then you know what a spinor is. That's basically what a spinor is. These are, you'll remember you have the 1, 0, 0, 1, so forth and so on. This is a very interesting thing there. No, I shouldn't go into that. Somewhere I have a whole book on spinners. So vector, tensor, spinor. Spinners are important for this kind of work. Actually, spinners, I think, are now used even in general relativity. So they've been expanded from what they originally were, which was, just something to explain spin. Then we have spin and statistics of elementary particles. That's a really interesting thing. We've got whole books on that, like this guy here's famous, PCT, spin and statistics and all that. So you have really interesting books like that running around. So you have different spin, or you have different statistics depending on the spin of your elementary particle. Right? If it's integral, if it's 0, 1, 2, then basically your statistics are called Bose statistics, Bose-Einstein statistics. And these give you things like Bose condensates and stuff like that. You don't have any exclusion principle with them. That leads to a different kind of statistics because you can have multiple particles in the same state, right? So you have a lot of particles in the ground state, and then you have fewer in the next possible state, and then fewer in the next possible state. So that's one kind of statistics, right? The other is going to be for fermions, like an electron or any other matter particle, something with a spin of 1/2, with a half integral spin technically, but basically it's 1/2, right? And in that case, we have the Pauli exclusion principle. What does that mean? Well, that means that you can only have one electron in each energy level in the system, right? So instead of having a more normal kind of distribution where you have a lot of things in a lower energy state and fewer in the upper one, you have basically pretty close to at zero temperature. At zero temperature, you will have one electron in each energy state, basically, up to the point where you get to the number of electrons you have, and then those higher energy states will be empty. When you have a finite temperature, some of these electrons will go up to even higher states and have fewer things down there. That's the Fermi distribution. So we have two distributions, the Bose-Einstein distribution and the Fermi-Dirac distribution. There's also one for classical particles, and actually I have a game called Quantum Dice, right? Well, it's not really a game. It's a game. It's a game for students, so that I made called Quantum Dice, all about those different distributions that I don't get to do anymore because I don't do modern physics anymore. Let's see. Then we have the year of discovery, 1932. This is what happens after the discovery of the neutron and all of the progress that's made after that, which is a whole lot. So now we have this idea that we can actually get inside the nucleus, right? So now we've got something really interesting going on. And that's going to lead to further things in the far future, but that's in the far future, not right now. Then we have the nuclear force and isospin. Isospin is a fairly weird idea, but this is, talking about something that happens for nucleons, for protons and neutrons, that is a little bit like spin. And so for electrons, right, if we had a couple of electrons, they have a spin, and they are interacting with a boson called a photon, right? And that's what's creating the electric field. In the nuclear force, what you have are protons and neutrons, right? And they're interacting with a pion, which is a composite particle. It's a meson. It's okay. We don't have to get into that in too much detail. And they have something called an isospin, which is what's interacting with that pion, which is a weird thing. Finally, now this is basically the end, right? Finally, we come back to lecture 11. This is going to go back to this Thomas precession. So it is Thomas precession. And it is 1/2. It's not 2. It's a factor of 1/2. So I was right the first time. So this is basically what we're going to look at for the this is basically coming back to something before. And the reason why it does that is because early on you don't really have enough of a background to really discuss it. So he comes back to this Thomas factor because of that. And then the last lecture, which is more or less just some other discussion about, random stuff, the status of physics in Japan between 1925 and 1940 and stuff like that. If that's something you're interested in, hey, there you go. It's right there. And so that is the story of spin by Sin-itiro Tomonaga. I really liked the book. Like I said, I believe I've read it twice. It's been a long time since I have read it, because I know this because I know this because this does not have any notes inside, so that's okay. So good book. I'll put it out there for you. Maybe this is not 1997. Let me see. Title 1997. Okay, so so it is 1997. For some reason, I got just looking, it's a cover photo, copyright 1997 for this guy. So very nice little book. I think you'll enjoy it if you're okay with the mathematics. If you're not okay with the mathematics, maybe you can look at something else. I'm not sure that there's something else that really talks about spin that much. I mean, that's a shame, because it's really, really a very important property of just about everything, right? So, we looked at the Zeeman effect in there. We looked at ferromagnetism. We looked at different interactions between different things. It's a very important part of the story of physics, and I think people should have a better education about it. And this is a good book for that. Again, it's historical. It's not really a textbook. However, it is also very mathematical, so it's not for somebody who's scared of math. Just to let you know. I don't want to put you off it, except, I do want to warn you before you pick it up. All right. So thank you very much for listening, and I will get another one next week. We'll see how the editing on this one goes. I'm trying something to get it better. I liked the sound quality better last time. It's just that there were some issues syncing. Now, obviously, there's always going to be another issue, right? That's the way the world is. Bye now.